to our talk. It's a very distinguished group of in the audience. We have like the elite developers are here. Just joking. So yeah, today we're going to talk about how to make pickling of closures in Scala 3 simpler and safer. And just a couple of words about ourselves.
Oh, yeah. So hello, my name is Jonas. I'm a PhD student at KTH, as said, and I work with data for streaming and actors.
Yeah, and I'm Philip Haller. I'm an associate professor at KTH in Stockholm, and my main research interests are in concurrent and distributed programming and also type systems, in particular capabilities and uniqueness. In fact, I co-authored the first paper on capabilities with Martin in 2010, so that was actually some very early work on this, but of course it has continued a lot, and yeah, especially in the last few years. Let's dive into the topic, which is closures, right? So let's talk about closures and also the environments of closures. So let's start with a very simple example. So here, we have a list of numbers, and we define a simple function below. It takes a threshold, and it simply returns a list of those numbers that are below the threshold, right? And so to filter this list, we use this blue lambda that you see here, okay? And of course it does what we would expect it to do. And one thing to note here is that this lambda here, the blue lambda, refers to threshold, right? And the threshold is not defined locally within the lambda, right? There's no local definition here within the blue part. And it's also not a parameter of the lambda, right? So that means it's taken from the so-called lexical context, okay? And lexical context just means textual context, right? So it's just textually, outside of the lambda, okay? Fine. Now there's two things to note here. One is that, what I just mentioned. So threshold is not defined within this blue anonymous function. And if you have such an identifier, right, which is neither defined within the lambda nor is a parameter of the lambda, then this is called a free variable, okay? So it's a free variable of the blue anonymous function. And now we can finally define what is a closure, okay? And we can actually use the original definition from Peter Landin from 1964, right? Which is that a closure is an anonymous function whose open bindings, which are the free variables, have been closed by the lexical environment. Okay, so the free variables, as in this case, threshold, is also called an open binding because it's not bound within the lambda itself. No, it's we need the lexical environment to close this binding. Okay, so what does it mean to close the binding? Of course, technically, what it means is that to be able to execute the lambda, the threshold value somehow needs to be sort of copied into the function so that we can use it when we apply the lambda, right? And so let's talk a little bit more about these free variables and what is captured, right? So this is actually what is called if we have a free variable that is closed using the lexical environment, it's also called capturing, right? So we capture a variable. So here is another example. It's just reformulated a little bit, where the function makeFilter returns the lambda. And again, as before, we have this threshold identifier, which is not defined within the lambda, and it's not a parameter. So again, it's a free variable, and it means the closure captures this. It captures the threshold variable. Okay, and so it means it must be made available somehow to the closure when we apply the closure. Now we can reformulate this further, so we can kind of change, instead of defining this anonymous function literal, we can also define in Scala, of course, a functional class, right? So we can define a filter class that extends a function type, int arrow bool, right? And then just define the apply method, and yeah, it just returns the bool, just like the lambda before. And again, in this case, well, we're kind of used to this style, obviously, because it's just a class with a method, and when we call the method, we just refer to the threshold, which is a field of the class. Okay, I mean, we're only writing it as a class parameter, which means it will be, you know, it's a constructor parameter, but of course, under the hood, it will become a field because, yeah, methods might refer to it. Okay, so threshold is a field, and obviously methods can refer to fields. But in a sense, it's you can sort of in quotation marks say that we sort of capture threshold as well, because it sort of becomes part of the environment, right? So we again have a situation where the instance of the class has fields that, you know, provide the environment that all the methods can use. And in fact, you know, there are ways to translate closures into such classes. Okay, Scala has had over the years different ways to represent closures, but clearly this is one way to actually represent a closure, is to create a class that has the environment, which is the captured variables in the fields. Okay, but it's not real capturing, because we're not actually defining a closure here. We're not defining an anonymous function, so that's why I put quotes here. And then the final example is here, where we're again defining a closure, an anonymous function, right? And in this case, we're referring to this field of this singleton object, and we assume that this is a top-level object, right? So a top-level object with a field, and that's what the closure refers to. And now the thing is, like, if you think about what does the closure need to do, like when we apply the closure, how can we get access to the field? Well, in this case, it's not an issue at all, because we just, you know, it's a global top-level object, so we can always access the field from anywhere, which means we don't have to do anything to make this field available to the closure, right? We can just, yeah, access it when the closure is executed. So that means that there is actually no capturing going on at all, right? All we're doing is, in the body of the closure, we're just, yeah, accessing a field of a top-level object, right? So in this case, we don't need to capture anything. We don't need to worry about it at all. Okay, so this will become important later when we talk about yeah, how to deal with the environment of closures. Yeah, but so closures, of course, we're used to them because they're very flexible. We can use them to write nice, concise code, functional code, you know, very declarative. But there is, unfortunately, trouble in paradise. So if we write code that is a bit more complex, like, for example, we might use Spark, Apache Spark, for data processing, right? So here I'm showing an extremely simple example where we're defining a data set, dist data. It's actually a distributed data set, which means this can be a huge collection of data, right? That is split across multiple workers, actually, in general. So this could be like, you know, terabytes of data. And of course, here I'm just initializing it for the sake of the example with a simple collection. And now the Spark has this nice Scala API that allows us to treat this data just like a distributed collection, right? So we have all the usual combinators, like map and filter and so on. And so here we're just using map to transform the data set such that, you know, we apply this lambda here to each element of the data set, right? So, and for this we use this very simple transform method, okay? This is, of course, just for the sake of the example. But the cool thing, of course, with Spark is that when we run map on a huge data set, the data is not moved, right? It stays on each machine, right? So let's say we use 10 machines to store and process the data set. What happens is we apply the closure on each part of the data set, on each worker, right? And the transformed data set, which is the value transformed, this is just a sort of handle to the transformed data set because the actual data stays on each worker machine, right? So that's what makes Spark so efficient, right? We don't send data around if not needed. Sometimes we need to send data. For example, if we sort of collect things, that means we collect the data on the driver program, and then we can print it and so on, right? But this is, of course, something you don't do very often because you don't want to transfer data if it's not needed. But so as you can see, this is probably the simplest example you can write in Spark. The problem is if you run this, you actually get an exception, okay? There's a Spark exception which says, there's a task that's not serializable. And, well, turns out the culprit is actually this lambda. Trouble with the pointer. And we'll see why this lambda is a problem. So, as I mentioned before, this data is a distributed data set. So each worker has a piece of the data. And when we execute map on the data set, this closure here, right, the blue lambda, needs to be sent to each worker node, right? So that they can run this on their part of the data set. Okay, but to send the closure, of course, we need to serialize it, right? And then send that to the workers. Now, of course, the closure here, wait, if we go back, it uses transform, but of course, using transform, calling transform is just short for calling transform on this, right? The this reference, yeah. And now, of course, if we with our knowledge from before, we see that this closure has actually a free variable now. Which is the free variable? This, exactly, very good. Good students here. So yeah, so this is actually a free variable now because it's not defined in the closure and it's not a parameter, and obviously it's not a fixed global binding like with the global singleton object. No, it's it's actually a free variable here. So we're capturing this, and okay, I mean, of course, we can capture things. That's not necessarily an issue, but in this case, when we want to send the closure, we need to serialize the closure, and that means we need to serialize all the variables that we're capturing as well, because they need to be, we need those to run the closure, obviously. So that means we need to serialize also this. And what's the type of this? Well, it's a Spark example, our example class, but that's not a serializable class, right? We did not arrange for it to be serializable, and that's why we get an exception when we try to serialize the closure, right? And this is not an uncommon problem. Like if you go through some Spark mailing lists, you see that this actually is not that uncommon. So just to summarize, if we use closures in distributed settings, it can be a safety risk, right? And lead to runtime errors, in this case, like serialization exceptions. And now what about concurrency, right? Concurrency is kind of notorious for, making our life harder. So let's check a small example. So here we have a simple scenario where we essentially have a collection of customers, and we just want to compute the average age of the customers, okay? And we do this using a future. So we kind of create a future to compute this concurrently, right? So concurrently with the main thread, we're computing this in a future. And what we do is we simply go through the customers, and the way this is set up here is that we have customer numbers, and we have a map called customer data that lets us look up a customer info record for, given a customer number, which is just an integer, okay? So we can look up the customer info and, use the typical flat map pattern here to collect the infos, the customer infos, okay? And then we can obviously compute the average age, right? Now, what's interesting here is that, well, we're accessing this customer data map that is not defined within the future. I mean, that's something that's, defined in the enclosing scope, because probably different parts of our code need to access that. And what we can also see here is that this is actually a mutable map, right? So this can be changed. So we can insert customer info records, we could remove them, we can look them up, and so on. But this means that since the future is running concurrently with other things, we can have concurrent accesses to this shared data, which is mutable. And if you have concurrent accesses to shared mutable data, you can get data races, obviously, right? Because you can concurrently, someone can concurrently read, and some other part in the main program, could could insert a customer, and then you have a data race, okay? So that's a problem, because that leads to non-deterministic outcomes. It can even corrupt the data structure and so on. So again, we have another problematic scenario, which is concurrent settings, right? It's again safety risk, because we can get data races, okay? So again, and that's again because closures, that capture shared mutable objects are highly problematic. Is there anything else? Well, closures are really cool. We use them all the time, but certain things that we've been trying to do, of course, also in Scala, is to actually connect, for example, a Scala JS frontend with backend running on the JVM, or on Scala native, for example, right? And so typically we're sending, objects and possibly closures between the front end and the back end, right? For case classes, this is the most common thing to do, right? That's the beauty of sharing code between the front end and the back end, right? But if we do this with closures, well, we need to have a portable pickling support, okay? And this is not obvious, okay? How to do that. So yeah, these are things we're going to look at. And in fact, this is the goals of this so-called Spores project, is to, well, first have the safety checking of closures so that it's safer to use them in a concurrent or distributed setting, and also to add some flexibility, okay? Just because we sort of deconstruct closures and sort of have more control over the different parts and so on, and that allows us to provide, for example, portable serialization, which is really powerful, and some additional features, like we can deeply clone closures and things like that. So there's a whole bunch of stuff we can do. So in a nutshell, a spore is essentially a special kind of closure that has two parts, right? It has a closed function, so that's a capture-free function, right? A function that doesn't capture anything. That's technically, it's called a closed function. And it has an explicit environment. And the environment can be constrained using type classes, right? And that's very powerful, because there's a lot of things we can now do. And in fact, spores are not new. I mean, it's kind of an old idea, right? It was initially proposed in SIP 21 back in 2013. And there's also a conference paper about this, actually. So there's lots of details there. Yeah, the original Spores had some issues. The implementation was a bit like brittle, not super robust, and there were some other limitations. So Spores 3 is kind of a revamp or a new take on Spores for Scala 3, where we use a new approach for type class based pickling, which is very robust and very simple actually. So the implementation is a lot simpler and more robust. But in this talk we actually talk about a lot of new things we can do, a lot of flexibility gains, because the original Spores 3 was presented by myself in a talk at Strange Loop 2022. RIP, was a good conference. And there's also a paper on this which has more details as well on the approach. But in this talk, as I mentioned, we talk about a whole bunch of new like innovations in the just released new version 0.2. So we created the tag this morning, so it's fresh. Yeah, it's very cool. So spores are now even more flexible, as we're going to show, including a demo. So you can partially apply spores, just like with normal closures. We support context functions, which is good because they can reduce some boilerplate. What's cool is that essentially we make computation on pickled data very simple now, which is really fun. It's like, yeah, you can do any kind of computation on serialized data, essentially, quite simple. Right, so now let's switch.
Thank you, Philip, for the great intro. So in the next, in the remaining time, I'm just going to show you like what does it actually look like, how do you use it. Then we'll have an example, which is like a very cool example. So, okay, how do you create a spore? I'm actually going to use my pointer. So here, so we're creating a spore here. We say we use the spore factory, and here we provide our closure, which is a function literal. So here we have the first parameter, which is x, has an integer, and then we just add 1 to x. So this is like a capture-free function. We're not capturing anything. But how do we capture something? So to capture something, you can write this instead. So here you would write spore 12. So we want to capture this value 12. It could also be a variable or like a y or x. And then the closure that we provide has as a first parameter would have to have the captured environment as a parameter. So here we say the environment has a type integer, which corresponds to this, and then we can provide the rest of our the function that we want to sort of create. Now, what you should note is that here this function has type int into int, right? But the actual spore has type into int. So the environment is captured and it's sort of hidden, just like a normal closure. Right, of course, it's the same thing. If you want to do context, use context functions, you can just use like a separate method. What's new in Spores 0.2 is the timer disappeared. In Spores 0.2, we have a way of automatically capturing things. So now you don't need to explicitly capture things. So what you can use is this auto keyword. And you provide your closure here, and this works. So internally, behind the scenes, we sort of make sure that this is okay. So to give you an idea, what actually happens is that we rewrite this function here that you have. We write it so that these two variables become parameters, like as a new parameter to this function. And then again, so the function itself is capture-free, but then we also then add these into the explicit environment, so behind the scenes. How do you use a spore? Well, you can unwrap it. So to unwrap a spore, let's say we have a spore which is a function from int to int. We can simply unwrap it, which gives us the value, and then we can apply to 12, for example. You can also import what you had in earlier versions of spores, just a way of interpreting a spore as a function itself, so we can apply it directly. Of course, like we saw a lot of these bad cases from Philip's intro on what can go wrong, right? So if you were to write this now with spores, so what happens here, we want to create the spore, but we're actually capturing this variable y, so this would give you a compiler error, right? So we don't have any runtime errors. Instead, we would get a compile error for this. This is a similar example to earlier. We have some class foo, then maybe a field or something of a kind. And then again, we're capturing this field. So our checks will flag this and say this is not okay. We cannot accept this. Okay, so those are two quite easy examples, but then things get a bit hairy when you like start to look at sort of all possible examples you could write, right? So what if we have this? We have some outer class, and then inside of it we have an inner class foo. Then here we return from this method, we return a new spore where we extend, we define a class bar which extends foo, and we return an instance of bar. So do we capture anything here? Maybe, maybe not. But actually, this should not be okay, right? So here we're capturing something like a reference to this outer thing still. Another tricky thing when you start writing, closures is these implicits in Scala. So, for example, this example where we have a method foo, which uses some bar and we return a spore. We might be doing something where we're summoning things and we don't even see it, right? Because implicits can be invisible to us, so we might actually capture things that we don't even see. So things get really difficult if you try to write capture-free code. If you try this out later, and you'll see like, you get a bit surprised at times to what you're actually capturing. Okay. To ensure that we can safely pickle spores, we simply disallow all of these problematic scenarios of capturing. And this lets us to ensure that once you have a spore, it's always safe to pickle and unpickle. It should never be a problem to do so. And to pickle, it's quite simple. You can use right now you can use the move pickle write and read, which we have here. So writing would give you a JSON string in this case. And then you can read it again from the pickle JSON string and use it as you would a normal spore. Okay. Right. So internally, how does it work? We have a macro for checking the closure itself. It's called check the body expression. And it has 4 phases. In the first phase, we collect all the symbols which might be captured. This is, all the identifiers, class definitions, and so on. We might actually have to ignore some special cases. If you have like a U here in this type parameter, we can ignore. And then in the next phase, we would remove all the symbols which are owned by the closure itself. So we remove all the local definitions, all the parameters, and so on, because these are like not captured. And then in the last phase, we just remove all the top-level symbols from this big list of symbols. And this would give us all the symbols which we need to consider as captured. Okay, and so, I think Philip also mentioned this, but just in a short, so the approach that we have is that the closures are capture-free. So we always make sure that these things that we want to serialize, 5 minutes left. Okay. And we do so by, how do we do environment variables? We do so by partial application. Okay, because of the time restrictions, I'll just do this slide and then I'll fly through to the example. Here, partial application is quite interesting. Let me go one back. Here we have a spore, and we can partially apply it to, for example, a value, and this gives us a spore. And doing so requires, okay, so this is nice. We can, we still retain a spore. So, partially applying it to 12, though, requires a given, which is a spore of a read, write, or int. Now, why do we need something like this? Well, we need to be able to, first of all, pickle this 12 so that we can capture it and pickle it. But what we do as well here is that we want to be able to pickle this pickler itself, right? So we want to be able to pickle the pickler so that we later can unpickle the pickler so that we can unpickle the pickled value 12, right? So that's, but this is really convenient. So when you later unpickle a spore with some environment, we don't need to know the environment type, right? We don't need to know this information. It's sort of stored in this pickled pickler itself. So that's quite convenient. You can also partially apply a spore to a spore. And yeah, so that's two. Same with the context. To create a spore read writer of T, it's quite simple. You would just, you can, if there is a read writer of T on a top level, you can simply summon it, right? So that's a quite simple way. So it's not too much like boilerplate you need to add to use this. Okay. Right, that's it. Okay, I'll just skip to the example. That's fine. Okay, so we have an example. I created this just for you know here. So we use Spores to serialize actor behaviors, where an actor behavior is a function. Okay. And what this does, well, you can like periodically serialize the execution state, and then you can deserialize it later on and recover if you've crashed or something. So I'm going to show you an example. It's the counting actor example. We have two actors, and one actor just sends messages to the second actor, and the second actor counts the number of messages it has received. Now, you'll note that it runs on JVM on Scala JS and Scala native, and let's see if I can boot this up. Okay, so we're running this example here. It's a counting actor. And let's see, I'm just going to open this as well. Okay, so I'm going to run it now so we can run it on the JVM. I'm just going to run it for a few seconds, right, or less. So we counted about 100,000 times here. Well, now we can inspect the checkpoint. So here, this is what the JSON representation looks like. We have a receive behavior. It's somehow we packed some environment. So what's the environment itself? It's like this integer 100,000. We can see the type of it, and here's also the name of the behavior class that's serialized itself. And the other actor has in its environment a reference to this the actor we just saw. So what we can do, we can actually now, if I open this, I can run this now on Scala JS. So now it's running on Scala JS. I'll try to stop it. Yeah, so what's interesting is we didn't start from 0. We were actually starting from, you know, the latest checkpoint. So we can, like, the closures themselves are portable in a sense here, right? And then the last thing we can do, the most fun, is to run it on with Scala native. So here we have a Scala native binary. Oof, do you see how fast it is? Wonderful. So it's really quite nice to use and fun to use, I find. So yeah, that's that. Let me open the slides again. Okay. So how do you? Okay, like now you have a. So maybe you have a library or you want to create some framework or something. How do you use Spores? So the way here we do it is that we have an actor behavior case class, and then inside of it, the behavior itself is a spore, this function. And how can you have a factory? So, well, one way of having a sort of a behavior factory is to have an inline method, which we call receive here. And then you can provide the function, which, if you look at it, actually the function is not a spore, right? So the user doesn't actually have to know about spores either. They can just provide this function. Then internally we just create a spore from it. All right, I'll hand back to Philip now to finish.
Thank you. Right. So yeah, I just want to mention that we also have some sort of preliminary results for like using micro benchmarks just to see the performance with regard to speed of pickling and also the memory size that's required for the serialization output, right? And so we compared the Spores 3 with Pickle, and with like Java built-in serialization, which is essentially object output stream and object input stream for unpickling. And so we see that we can actually get some really nice speedups. So these micro benchmarks, there's like a handful of different kinds of closures, right? But we get, speed up to 5.4 times, which is quite a lot. And also the size reduction, which means the number of bytes, which is the serialized data, right, is again between 2.5 times and 9.2 times difference. And yeah, if you want to know more about the details, we have them in the full slide deck included that you can check online. Yeah, so in summary, Spores 3 are designed to make closures safer and simpler to use and to pickle and unpickle. And we have very strong checks for the environment to enable this safety and also to add all this flexibility. As I mentioned, apart from pickling, we can also do deep cloning in a safe way where it's ensured that the cloned spore does not share anything with the original spore, which is very good for concurrency, for example. And yeah, version 0.2 is out now, so check it out. We have a whole bunch of examples, also like a workflow implementation and things like that. And also the durable actors example I think is fun to play with. And so yeah, that's our talk. Thanks very much for coming.
Thank you.
Okay, I'll start with the first question. Thank you very much. You mentioned it like I think in one sentence, so I just want to confirm you can use any sort of serialization format. So if I want to pickle to JSON, then I could also do that with that library or no?
Yes, I mean, we support everything that Pickle supports at the moment. So okay. We haven't, it's kind of, at the moment, yeah, it's tied to Pickle. We have some ideas of how to make the serialization framework pluggable, but at the moment it's sort of limited to what Pickle supports.
But that one supports a bunch of things. So.
Yeah, exactly, and yeah.
Okay, any other questions?
I'm not sure if I will be able just let us pretend that we have some chain of futures. I'm a game developer, so my character first go to someone, then picks up an apple, then moves somewhere. So this is represented as a chain of future. And when I want to save my game, I need to serialize this behavior. And this is very difficult for me. So I came here hoping that those spores might be able to do this. And I think they might, but I'm kind of afraid that I will make my definition of the character behavior much more difficult, because now it's just I write the futures and it's very simple. Yes. So is it possible to express this with spores without being too much explicit, without because you mentioned some implicit conversions from lambda, so I don't know if you need more.
Good question. So, I mean, maybe you can elaborate a little bit on this, because you mentioned.
Yeah, I think so. So I experienced, I'll say, like a big motivation of this was a similar problem. Like I wanted to be able to do continuations and serialized continuations. And this was just so difficult. You end up capturing things and they always crash and so on. So I think it's the best way of doing it right now, and but maybe we can improve. It would be great if you tried and then we see what we can improve still.
But I think the key is really this, right? Because this is really the example, right, where you basically, in your API, for example, your game engine, right, to express the behavior in your game, like you write normal functions, like the green one here, right? There's no spore here. It's just a context function and so on. So this is what you would write in your futures. Plain Scala functions, right? Let's say.
This is actually not, because what I would be writing is future, go to something, map, go to something, map, pick up.
Yes.
So there are no declarations, just the future bodies.
Yes. Oh, I see what you mean. Yes. Okay. Right. So maybe I guess.
So I tried to implement a future runtime as well. I can share a link with you later too. So just to how it looks, but also the actor behavior, so the behaviors are nested. So you have the same issue. Like, how do you deal with nested behaviors?
But basically, yeah. So Jonas actually created sort of durable futures, like futures that you can just serialize.
That's exactly.
So he has an example, yeah, how to do it. Yeah.
So it's in work in progress. So
I don't know the state of the.
Oh, yeah. I'll share it with you. So, but maybe some more questions.
Okay, so we're out of time. So let's thanks Jonas and Philip again.
Thank you.
Thank you.